So good afternoon. My name is Mario Gerla at UCLA, and I'll be talking about vehicles and how we can use the cloud for some of our experiments. Is this working? Oh, okay. I'm sorry. Of course. Excellent. So, in fact, some of the work I'll be describing is based on our project, NSF project. The title is very long, but the key words are pollution and congestion, and this is cooperative with Rutgers and UCR. And in this project, we identify a number of experiments I'll be talking about and in the course of the presentation. But the goal of the project can be summarized by this slide. And so we are looking for safety, mobility in the sense that we want to untangle this kind of congestion and want to reduce the pollution in the environment. And our task has been actually made a bit difficult during these past 3 years because many things have happened in the vehicular environment. First of all, the Department of Transportation, at the end of a long connected vehicle program, agreed that V2V is good for vehicles, so now everyone's jumping on that. Until last year, there was an uncertainty. So, and the second thing is the autonomous vehicle. All of you have seen the Google car, and that will put some new requirements in the design of distribution networks. Volvo, as and other truck companies, have been using the concept of automation in platooning. So now that also is something to account for. But at the same time, as the vehicles will become increasingly automated, all the vehicles will do some kind of platooning. So this new environment creates a new set of problems that we can address. For instance, delivering entertainment to the drivers, impossible before, but now that the driver doesn't have to drive, that's an important issue. And in fact, there is so much intelligence now built in the cars, like the Google car has about 100 sensors between cameras, lidars, lasers, and so much information is collected and processed on cars, and that we can really talk about a vehicular cloud, you know. So a vehicular cloud that processes some of the data and performs some of the functions that conventionally would be done in the big cloud. So there will be the issue of trading off vehicular versus big cloud. But let me just get directly into the problems that we're interested in. The first problem is the platooning. So vehicles eventually will be platooning to allow drivers a more comfortable drive. However, this platooning is possible only if there are efficient communications between the cars. In fact, if you look at this picture, today cars are maintaining the distance from each other using laser and lidars, and it has been proven through experiments and also models that that is not sufficient to avoid crashes in adverse traffic conditions. You also need the cooperative communication capability given by V2V. So the first experiment will be to look at this environment, but go a bit beyond the simple platoon, looking at what happens when you have multiple platoons across several layers, how do they interact with each other, and there will be issues of stability, and also issues of attacks, because somebody may attack, and how do we go about correcting the problem. So as we go to multiple platoons, the issue of scalability, so that's where the cloud comes in. Let's move on to, however, platooning alone doesn't solve the problems of major congestion. In fact, what happens is that when many platoons together converge on these lanes, they may cause what we know as shock waves. So traffic stops and then speed up and so forth. And that is very dangerous because what we done some simulation and discovered that if you take a snapshot at a certain time, you see that depending on along the highway, there are segments where the cars are practically stopped and then speed up and so forth. And this is what causes most of the accidents. By introducing V2V, we are able to reduce this phenomenon. As you see here, with V2V, you have improved the situation. So now the question is, the protocols are totally distributed, of course, because you have no time to go to the cloud and get instruction on how to control the vehicles. But the study will require adjustment of the parameters. So we are talking about what Kate referred to as the big instrument. We want to use the cloud as an instrument to do the fine adjustment of the parameters to optimize the system. Another important area is, of course, traffic management, because we can certainly smooth the traffic on one lane, but eventually the network will become congested, so we want to reroute the traffic. Most of the navigators today manage to find improved routes, but they do not solve the problem of route flattening. In other words, everybody moves to the next route and back and forth, and I'm sure you'll experience that. So that's where the cloud can come in. It has more information than the conventional navigators, and it will be able to dispatch traffic, in this case, on multiple paths using computational techniques that require some processing of the cloud processing power. At the same time, we discovered that it is useful to have the user themselves optimize short-range trips, kind of micromanagement, instead of going to the cloud if you want to figure out how to get around the corner because there is a double park truck, don't want to wait 5 minutes for the optimal solution. So one of the issues that we want to work with is the interaction between the optimal computation of the cloud and the local computation of what we call the mobile vehicle cloud. Now, one thing that the autonomous vehicles bring in is the fact that the drivers are distracted. So this makes the vehicles and the convoys prone to attacks, and so malicious individual organization can really cause chaos by penetrating cars and disseminate wrong information. So we have looked at the problem. We think that the cloud, the Internet cloud, NSFCloud, will be able to help in giving some overall information about the traffic to vehicles and so forth. One last problem is the pollution. So we have 3 teams. Each of them has been doing measurements in their environments. So these are measurements collected in New York City by Rutgers. So they were trying to correlate the CO measurements with congestion, and there was a very good match until they found this strange situation here, Battery Park, and the reason is there were roadside vendors there keeping their engines on, creating a lot of CO. So anyway, this demonstrates the importance of doing experiments to understand what's going on. The sensors are in this kind of box. Experiments are done also at the riverside. In this case, we're concerned about pedestrian navigation because the pedestrians are the ones who suffer the most from pollution. So the riverside was able to develop these models using the car emission. The interesting thing in this picture is that it took 4 hours for a desktop to generate a pollution map. Now, we would like to do this interactively so that when you go jogging, you know whether you should just go one way or the other. And notice this pattern changes very quickly with the atmospheric condition. In fact, the team at UCLA, led by an atmospheric science professor, did the correlation between the aerodynamic phenomena. Here you see the air flows in the streets and congestion. So in the morning, there is no problem. As you build up in the afternoon, you see some very interesting situations. And you see the pollution at the same time, varies depending where you are. So to conclude this, you see from these examples that there is a need to have cloud, develop, maintain these models, and interactively. Okay, thank you.
Yeah, I need the box. Yeah. Okay. Good afternoon. This is your third UC talk, so it's kind of random, but we started Irvine, LA, and now we are in Santa Barbara. And this is work that we've been doing for a while now with my colleague Divi Agrawal. And basically, I want to give you a flavor of the type of work that we are doing and the type of experiments that we run, and hopefully we'll be able to exploit the various chameleons and the cloud labs. This is the picture that I have. So we are much lower down than the two previous talks. You have on top the analytics, the games and all of these. And then at some point you have the infrastructure where the data is actually stored. And this data structure, this data is big and scalable, so you put it in a big data center. You want to protect some of it, so there are serious privacy issues. And because one big data center, you know, this is huge. You need a bicycle to go around it. So it's a real big distributed system that we are working with. But this big data center can actually fail also because of natural disasters. You can have a hurricane, etc. So we need to explore georeplication. So all our research has been a lot of our research has been at the infrastructure level, trying to understand and develop protocols for this purpose. So I'll start with an example of some of the work we did at the inside of a data center, and this is a system called MAT. And here I will just illustrate for you the type of problems that we are trying to explore. So for example, we have an optimistic concurrency control approach and a pessimistic concurrency control approach. They represent different alternatives: high throughput, low latency, high aborts, low aborts, etc. We would like to be able to, in a cloud setting, do experiments that will expose this. And we propose our own protocols, and then we see how they perform. So for example, we want to have high throughput and high scalability and low aborts. So we have a protocol which is MAT. It was developed in the last 2 years, and basically it's an optimistic concurrency control protocol. So it's different from a pessimistic protocol. It presents different trade-offs. It uses a timestamp approach to figure out where to serialize transactions. So we use an approach where we have a proposal and then a value comes back, you have a validation phase, and then eventually you decide on where a transaction is going to come in. We experiment with this, and we want to compare this protocol with other pessimistic protocols, for example. Now I'll give you another type of problem that we work on, where we are interested in georeplication. So in georeplication, we have data centers across. So I'd like to use the data center that is in Indiana, the data center that is in Chicago, the data center that is in China. Actually, we are interested in global replication in general, because the problems of latency that came up in the first talk actually is very important in this case. So there's a system that was proposed a couple of years ago by Google. It's a distributed spanner which manages georeplication consistently. It uses, so you need to have consistency. So you're going to have a notion of a transaction. You need a two-phase commit protocol. Underneath it, you have a storage system which is replicated. You're going to use a consensus protocol. You'll use Paxos. So they are sitting on top of each other. These are heavy-duty protocols. These require rounds of communication. In a context like this, where we have, okay, in the US, maybe we'll have round-trip latencies of 20 milliseconds between two different data centers. However, if I replicate, these are numbers we took a year or two ago. Ireland to Singapore, it comes up to over 300 milliseconds. If I'm doing a two-phase commit protocol or consensus protocol like Paxos with 2 rounds, we are talking about seconds, which is perceptible. So this is the challenge, but we want the consistency. You heard Magda's talk at the beginning. There are applications that want the consistency. So the challenge is how to work with this and how to develop environments that work in this environment. And we need experimental setups to solve this problem. So for example, we looked at this particular problem and we said, okay, where is the expensive protocol? It turns out in terms of communications, it's 2PC, the two-phase commit. So we flipped the picture around. We executed Paxos to replicate transactions, and then within each data center, where latency requirements are low, we can execute two-phase commit. And we have good results, and we would like to, we compare them. At the moment, we're using AWS, and I'll get to that. Another problem we face when we talk about big data is variety. We have lots of different types of data. We have different representations of data. We would like to support all those types of representations. I've been talking about replication now for fault tolerance mainly or for performance. Alternatively, what we are exploring is using replication for representation, where the different copies are represented in different ways. So I could use a column store if I'm doing OLAP applications, aggregation. I can use a graph if I'm looking for face-like applications. But it might be representations of the same data that I'm using across. Again, this is another context where we want to, okay, I'll have to run. So we are basically using a replication approach to manage all of these together. Privacy obviously is a big thing, and once I give my data to a cloud, I want to make sure that it is secure. There are 2 problems here. One is that the data needs to be encrypted, but then I want to make sure that it provides functionality. I'm a database person, so I want to be able to do operations. The cryptographers have great techniques. They are expensive. The challenge for us is to come up with ways of using them, trade-offs, and doing experiments that expose the leakages as well as the performance benefits. There are significant increases in storage that once you encrypt the data, the storage increases, and not only that, the communication overhead increases. Okay, now Kate asked for what kind of experiments are we trying to do and what are we looking for? So we are looking for single data center experiments. We are looking for multi-data center experiments. We want to have virtual machine access as is given by Amazon, but I wanted without paying all the money that we pay AWS, frankly. You already said this, so this is great. We are very interested in standard benchmarks. So we have our standard benchmarks that we use in a database context. We're interested in looking at evaluation of contention, throughput, latency, scale out, and handling failures. I want to be able to say, I'm going to fail this and still run. So a wish list, VM placement control. I want to know where my VM is sitting. It's not wherever AWS decides to put it for me. I want to know more about network utilization, physical machine utilization. Basically, we want EC2 with more control and monitors. I'm done. Thanks.
Hello, everyone. My name is Zhenhai Duan from Florida State University. The title of our project is toward private cloud storage in public clouds. So exactly what we try to do. The focus of our project is on user privacy. I think I just mentioned before. Actually, we have a more precise problem we try to solve. The precise one is that to what extent and for what kind of cloud service we can keep users anonymous from the cloud providers. So basically, I don't want the cloud provider to identify my physical information. This is what we focus on. So of course, there are already some existing schemes on preserving user privacy. Most of them focus on like a client-side data encryption to make sure that the cloud provider do not have access to the real data. Okay, but of course, this do not protect uh, the physical personal identity. For example, the IP address, the credit card number, and bank account, etc., can often be identified. Okay. There are also some work on privacy preserving identity management, but normally it requires some centralized trusted party, which present a single point of failure, and also we need to trust that party. If that party misbehave, then we are in trouble. Okay, so to properly address the problem we want to solve, we believe there are three areas we have to consider. One is that we still need a way to properly authenticate users by the cloud so that we can have proper access control. Another one is payment. Okay, for many services we still need to pay, of course, to the public cloud. Another one is how the users communicate. So this is how do I access service from the cloud. So what do we propose? What we propose is a decentralized, anonymous payment, authentication, and communication system, the DPAC. Okay. So basically, DPAC capitalize on a number of advances, basically recent or not so recent. One is on the anonymous authentication, in particular, anonymous credentials. Okay, so basically, normally use techniques like blind signature and zero knowledge proof, basically to provide a function that a user with approver can show that it knows or possesses some value, but without giving the value itself out. Okay. The second one is anonymous electronic cash, like I'm not sure how many of you know, like a zero cash. That is an improvement over Bitcoin. So basically, it's to improve the user anonymity during the transaction in Bitcoin. The Bitcoin cannot trace back to the user. Okay. The third one, possibly most people you all familiar with anonymous communications like a Tor system. But of course, we have some other requirement. In particular, is bandwidth. We have to support like a high bandwidth communication. Okay, Tor probably is very relatively weak on that. So that figure illustrates the basic kind of architecture. We have cloud. The middle part is a DPAC that we develop. Okay, the end users will access the cloud service through DPAC. Okay. So what we need for the experiments, in terms of experiment, basically the previous figure shows the components we need in running experiment. We need some cloud. Basically, we will extend existing cloud software, OpenStack, to support the interaction with DPAC. Basically, the 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 cloud side must support the authentication, payment, and communication we mentioned. But of course, communication part is minor. Major thing is the authentication and the payment part. They must support it. Okay. DPAC is, of course, a major part we will develop. In our design, basically, is kind of like a peer-to-peer system, but we use more, we call it a super node because the function we supported kind of uh, a lot of functions related to payment, related to authentication, etc. So more complicated than normal nodes. Okay. So basically, of course, everyone can support this feature to join DPAC, of course, of course, including the cloud providers. They can participate. Okay. From cloud we need, for experiment, we also need a large number of users, okay? So this part, ideally, we would like to have a diverse set of users, access device. Um, of course, people access cloud using different device. They want to emulate that behavior to see the complexity of our system and the overhead put on the system, etc. So based on my understanding of the NSF cloud, we believe like first two can be to a degree natively supported. Of course, we will do the software part. Okay. For third part, I believe we can also use some nodes because the bare metal servers are provided. We can use that to emulate users. But of course, in order to support like different capacity CPU or different access device, uh, preferably we want to have some mobile device, etc. But as mentioned, we can use the federated model using some other, either we build our local testbed to join, or we use, as mentioned, Genie as some mobile device support. Okay, actually I'm done, so I'm early. I put it back on the table.
We even have time for
Hi there, I'm Andy Bevere at Princeton University. Today I'm going to be talking about OpenCloud. Larry Peterson is the chief architect of OpenCloud. It's a joint venture between Open Networking Lab and the Planet Lab group at Princeton. So let me tell you about a research question that we want to ask. So if you go to Amazon Web Services console, it looks something like that. And you'll notice that the Amazon Infrastructure as a Service Cloud, EC2, is right there. It's just a small part of what they offer. So the rest of this is this ecosystem of services that are accessible to you. If you're building an application on EC2, you can go out and use these services as building blocks, cobble them together to build your application. And this is a really powerful idea because it helps you move quickly and focus on the value added of your idea that you have. So the question we want to ask is, how can we help the research community create a similar ecosystem for research projects, research services? And it seems to me, okay, that this ecosystem could not only be for the distributed systems and networking community, but it could be much broader to involve services that scientific community would use to do their work. And this could be really important from the standpoint of, one, it could help people move faster, make it easier to explore their research ideas. It could lead to better visibility for research projects, easier to go out and find users for your research. Other people could pick it up and use it as a building block. And ultimately, I would hope that it would help researchers have more impact and NSF to realize more value from the research investments that they make. Okay, so let me describe the experiment that we want to run. So we want to build and operate, well, I said meta cloud, but Rob used that in a different sense earlier. I'll say a logical cloud. So OpenCloud is going to support long-running services, kind of in the style of Planet Lab. Integrate with lots of different resources, so commodity clouds, NSFCloud, and other testbeds like Genie and Planet Lab. And it's going to span data centers and networking resources and edge sites. So it's got this unifying architecture, this novel cloud architecture, designed around this idea of composable services and based on this key architectural principle called everything as a service. And to do this, we're going to, of course, leverage open source software, including OpenStack and some other pieces that I'll tell you in a minute. So the challenges here for our experiment is really creating the right architecture and the right abstractions that'll let us help bootstrap this research service ecosystem. Okay, so the architecture of our system has basically 3 layers. So at the bottom layer is an SDN layer using this component called OpenVertex. This is something out of Open Networking Lab. It's the successor, from what I understand, to FlowVisor. So the abstraction provided by OpenVertex is SDN-enabled virtual networks. So you can get a virtual network connecting your VMs and plug your OpenFlow controller into it, control the control plane of that network. That's the bottom layer. The middle layer is OpenStack. Everybody's familiar. It's easy to build a development cluster for OpenStack, but we want to build a production multi-tenant cloud, actually multiple of these, that support best practices in security and availability and scalability. There's a little bit more work to do here. So that's the middle layer. The top layer is XOS, which we think of as a cloud operating system. So XOS raises the level of abstraction of the underlying infrastructure, basically OpenStack. So the focus of XOS is on services, so managing services, orchestrating services, composing services into new services, scaling services. And it's designed to be extensible. So when you have your service that you want to contribute to this ecosystem, you can integrate it into XOS. You can leverage the abstractions that XOS provides, and you can add your own new abstractions for users of your service. So XOS, OpenCloud is a logical cloud that combines together resources from lots of different places into a single unified system. And so it's orchestrating resources at data centers like NSFCloud, at network POPs in Internet 2, OpenFlow switches and backbone networks, edge sites, and also commodity clouds. And the idea is that service builders can place functionality wherever they want in the spectrum, right? All the way from the data center to, the fog at the edge of the network. Okay, so let me take a step back. So we have this novel cloud architecture and abstractions. We want to validate it with real users by running this cloud. If we are right about the value of this architecture and abstractions, then hopefully we'll be able to bootstrap this research ecosystem. If we're wrong, well, we've still built this infrastructure as a service cloud that's SDN enabled and people can use it. So, I mean, there's still value here in OpenCloud, even if it turns out that our intuition about this research ecosystem doesn't pan out. So what do we want from NSFCloud? What are we looking for? Well, we're trying to run a cloud in the long term, so we want long-term resources, hold them for quite a while. So we're looking for basically clusters of bare metal servers at multiple sites, and we want programmable OpenFlow networks between these sites and within the sites. we want some amount of dependable bandwidth between the clusters. And also, we hope that our research is successful and we can grow over time. So I think we can start pretty small. I made up the number of 10 servers per site. Maybe we don't even need that many because these are really beefy servers in a lot of cases. But we can start small. But we hope that there's a path for us to expand when we see growth in our user base and in our services, that we would like this elasticities from the platform so we can just kind of scale up. So here's a URL. You can get more information on the project, and that's it. Thank you.
Hi. Okay, so I'm Jack Ling. I'm assistant professor at the University of Pittsburgh. And the work we're doing is probably more low level than what we've seen so far. And that we're actually looking at how you design the underlying system software, operating systems, and virtualization layers to support cloud computing in a consolidated environment. And what we're particularly interested in is looking at the issue of workload interference on a single node in a cloud, how that reacts to scale as you put in large applications running across an entire cloud environment. So I should say there are two approaches that you see when you're looking at how you're dealing with interference in a cloud. The two popular ones here are basically modifying the application, mainly by replicating computation. You see this at Google, their tailored scale article in the communication, the ACM. And then you have what EC2 does, which is basically give you dedicated that no one else is going to run on. So we're looking at that sort of thing, but what we've identified is that that's not nearly enough, and that when you look at this, you actually have to take into account the system software as a source of interference. So the standard approach you see is basically you just take a multi-socket machine, break it across the NUMA zone, basically applications on an entire NUMA domain. So you have segmented so the memory bandwidth, and you don't have cross-memory contention or anything like that, and the applications run in their own zone. This is support for this, but you still have interference that exists when you start looking at having to deal with internal OS services. So how do you access a common resource in the OS that is contingent upon by both the zones? This has the effect of injecting interference into what shouldn't be interfering at all, what should be purely isolated. So what we do is that we actually look at how do you take that approach I just showed and actually implement that at the software layer itself. So what we look at primarily we call multi-stack approaches, where we take commodity environments, commodity Linux environments, and break them apart and run custom system software, custom kernels, custom VMMs on dedicated hardware. And the two things we look at primarily are how we do this dynamically. So you can actually dynamically take a node, partition across multiple resources, and allocate, say, a CPU, multiple CPUs, some memory, some devices, and run an entirely separate kernel to manage those devices and resources. At the same time, we look at how do you actually move workloads across these partitions at the software level, basically to react to what isolation requirements are. So again, the implementation of this, there's multiple examples here that we look at. These are just a few. But again, what we look at is designing and implementing custom software at the base layer of the hardware from the bottom up to basically provide isolation. So just a couple of examples here. We've done this in some instances. So the Palacios VMM is the virtualization layer I wrote in grad school. Basically, it's designed for high-performance environments and provides isolated virtualization containers for VMMs. It's a full system virtualization thing. So it basically works just like KVM. So you have the option of either deploying on something like KVM or Zen or deploying on Palacios at runtime and basically gaining different levels of isolation as the application requires. We've taken this and coupled Palacios with Kitten, which is in this case a HPC operating system that we've developed with San Diego National Labs designed for supercomputers. What we can do is basically take of the hardware and partition it dynamically and boot up this separate kernel running either native applications or running the Palacios VMM with Linux VMs on top of that, again, providing full isolation for the different containers. So as far as moving on is what we would want from this test bed. So I think the best example is show what we're limited to right now. So this is an experiment we ran and shows the limitations of what we've been able to do. So this is a simple scalability study of looking at how well we can actually isolate workloads on our example platform as we showed. And the goal is, again, how much isolation can we provide from, say, just a stock standard Linux environment. So the 3 lines here, it's hard to read, I apologize, but what we're essentially comparing against is just running an application natively on Linux using basically space sharing as implemented by Linux. Same space sharing is implemented in KVM, and then running in a virtual machine on top of Flashes, on top of the Kitten kernel that we custom built. And the results we see here is basically as you look at scalability increases, we can provide native performance for our applications, assuming just a dedicated node. But as soon as you add in workload interference on the commodity side, where essentially we just ran Hadoop on Linux natively, and then on the separate NIMA zone, we ran either a VM running an HPC workload or that HPC workload natively, we could actually outperform native in a virtual machine. So the limitations here is we don't know how well this does. The scale here is pretty small. The scale you typically want for a benchmark such as this is on the order of 1,000 nodes. I can't afford that. I have no way of getting access to that. And when you talk about custom system software, it's pretty much impossible to convince any large-scale system operator to actually let you come in and replace the kernel or insert a kernel module. It's just not something you can really do. So I was all prepared to come here today and basically beg for something like just sudo access. But from what I've heard, it sounds like I'm going to get a whole lot more than that. So I'm actually pretty excited about this. So the ability to actually run custom system software, at least for the work I and others do, is incredibly important. So I thank you for that, and can't say how much excited I am because we actually will be able to look at this in more detail. I can say that from experience, there are some things we probably need to add here. And first one would be sort of debuggability, right? So when you're actually implementing custom system software, as soon as you move to a new platform, you've got a lot of issues you have to deal with. Lots of devices you haven't seen before, chipsets you haven't seen before, lots of stuff can go wrong. So one of the things we run into is how do we actually develop a system software environment that can run on these platforms you're building? So we would need some support either for getting a dedicated node that we could just use for debugging and implementation, and we'd need it for probably a long time, just full access to. Another thing that would be very useful is if you could come up with a hardware reference platform to say, these are the devices we're using, this is the CPUs and the features and all of that, and either you can go build a system yourself that has this, or hey, here's this cheap single node, and maybe it's not the full-on node, but it's at least the components of the node that we could buy ideally inexpensively and just run locally. So that's, again, critically important as far as getting this up and running. The other thing that would be very helpful for us is partitioning at the hardware level. So when you look at the interference effects, one thing we really rely on is being able to actually take hardware resources and dynamically partition them up into isolation domains. So there are a number of things like NUMA is the obvious example here. Things like SRIOV or IRMUs, these are all very critical. And if you look at new basically architectures out there, I would hope or ask that you actually look at how do you actually partition these, how can you break them up and assign them potentially to different enclaves or different operating system runtimes to actually make use. And finally, I would say that one of the main issues you see in system software development is workloads, right? So what should we actually target? It's very difficult to actually develop a system, and we're just, I don't want to say we're guessing, we're making an educated guess as to what the applications are, but that's really not our domain of knowledge, so we're sort of hoping that we're right. So one of the things that would be very helpful here is if you have this environment where a lot of people are using it and running applications, if there's some way of actually giving access to those applications, system and software developers like me, that we can actually say, okay, this is what we should target, or this is what we can study to figure out what's going on, right? So one of the things we really would like to do is understand much more where interference is coming from, both at the hardware level and the system software level. So if you could have, say, just a default image that people could run applications on, it's pre-configured with, say, like kernel trace points and performance countermeasurement facilities and all that, we could just take their application, instrument it ourselves on the cloud platform, and just try to see what's going on. And then we could modify that with, say, our own custom software and see if that changes anything. So that'd be very helpful. And I'd also say that build off on this, it'd be nice if we could talk about, say, collaboration between application developers and system software developers, because there's a gulf that seems to exist between those. And I think architectures like this would be helpful as far as getting people like us talking more. So that's it for me.
Very clear articulation of requirements, saying so much.
Okay. Oops. I'm also lower level than some of the earlier talks. My name is Kirk Cameron. I'm from Virginia Tech. I've done some of this work with Ali Butt, who's also in the audience. We're told to introduce ourselves. I run a center called Stack, which we try to look at hard problems to solve across the stack. And I'll talk about one of them today. I've also done a few things. My work goes back to and is motivated by energy efficiency in the data center, which we did about a long time ago now, starting around the year 2000 or so. I've also been, so some of my research has resulted in a company. We had about 500,000 users of our freeware not that long ago, and Spec Power and Green 500 I helped start. So I'm a performance person by background, and so just like these folks at Amazon and Google, I care about performance a lot. And it's important to realize that we don't do a lot of things in the data center and HPC centers because we are afraid of the effects they'll have on performance. And even small loss in performance that you see here, these examples from Amazon and Google, are reasons for us not to do things like employ energy management, for example. Because we don't know what the effects will be on performance. So a lot of my work has been focused on trying to develop a deeper understanding of the relationship between performance and power. And I'll talk about that a little more in a minute. So, for example, the conventional wisdom. This is just a plot of the Old Republic game, looking at various microarchitectures at different frequencies and different designs and how they perform. Because a lot of the gamers are obviously very interested in the performance that you'd see versus clock scaling. And those of us who are old enough to know how to be overclockers, like I used to a long time ago, know what this means, right? We usually generally associate higher performance with higher frequency. In fact, microarchitecture until about the turn of this century was really focused on increasing frequency. Only recently have we adopted the multi-core paradigm. That's the conventional wisdom. But about 10 years ago, when my research group started ramping up on energy efficiency work, we saw some anomalies in the work that we were doing. We saw basically that sometimes you would slow down the processor frequency and speed up, and performance would increase. And we chalked it up because the reality is like, here's samples from about 35 publications that other people have done. None of this is my work, but my work reflected a lot of this back in 2004. But you see small losses in performance when you scale the processor speed, which was indicated. Yeah, these were repeatable experiments. These aren't just. That's why they appeared in publication, right? They actually were repeatable. And so I promised myself we would revisit this, and we revisited this a couple of years ago, and now I think we're making some serious progress. We in the literature though we look and if you classify those that literature that you just saw a second ago, you'll notice that we see smaller slowdowns, we usually refer to them as, or unintended consequences of speeding up the the processor speed. In hardware, we see 2-3%. When in communication, when we have heavy communication workloads, we see slightly larger percentages. It's a little more. There's a dichotomy of performance in software, but then if you run I/O benchmarks, the slowdowns get huge. And that is counterintuitive if you think about it, because typically the I/O performance is not bound by processor performance, right? We're usually bound by the I/O subsystem. And yet we saw 68%, 14%, 40% slowdowns when we speed up the processor frequency in I/O workloads. And I should mention that this work just recently got funded by NSF, and thank you, NSF. I think you're here. So anyway, I don't have time. This isn't, and Kate wanted a specific structure for this talk, so I tried to adhere to her suggestions. But let me just show you some of the results that we have there in publications from this year and pending publications currently. So what we were doing basically was we had to do it was a very large problem space. You have all these different various processor frequencies. You have different file subsystems. We looked at ext3 and ext4 in particular because they're open source and we could dig down in the source code. You're looking at these very complex systems with lots of different parameters that you can change. The workload can change. All the workloads we had to run, for example, number of threads in an IO zone workload from 2 to 256, mapping them differently across the cores that we had available to us in the system and so on. All these different variables. Hundreds of thousands of different cases that you can run, and you'll see these slowdowns in maybe 5–10% of them. Not only that, I'll talk about in a moment that the system variance is very high when you're in with I/O, and so you have to run these things dozens and dozens of times to get a number that you can believe. And so what these results show in the upper left-hand corner here is varmail, which is basically representative of a web server workload. And what you see from left to right is the changes in clock frequency on a typical system we have in the lab, from 1.6 to 3.1 gigahertz. And that's normalized performance. So basically, as the lower that the plot line goes, the worse the performance is relative to the slowest frequency. So what that graph shows is that the best performance is at 1.7 gigahertz for this workload, and the worst performance is about 2.5 gigahertz. So just increasing the clock frequency will not give you better performance. She's giving me a signal. I've got 547. Oh, all right. I'm keeping you honest. All right. So I think I have plenty of time because this is like second to last slide. Anyway, so performance goes down, right, as the clock frequency goes up. How much? In this case, if you were to select, so we're doing this statically. We're maintaining the clock frequency at a static state the entire run. And we're doing that because it just simplifies our analysis. The reality is that you're running basically some form of a scheduler that's changing the clock frequency dynamically, so it's much harder to isolate these problems. So if we fix the clock frequency at these states, we'll see that there's a 14% performance drop if you start at 1.7 gigahertz and drop to 2.7, right? We created a runtime system we call LUC, which limits the unintended consequences, and this is the subject of the paper, where basically we figured out, we took a deep dive on the Linux kernel, on the applications themselves, everything along the critical path, the performance of these things from hardware to software, all the way across the stack. We figured out that the problem really was, it's not a bug in the Linux file system, but it has to do with, there's some queuing theory behind this. So basically it has to do with the way that threads are organized and there's some false sharing that gets introduced when you increase the clock frequency that you don't have when you decrease the clock frequency. And so our LUC system, runtime system, basically reduces those differences. In case you were wondering if we did it across other workloads, this is on the bottom part of this chart is OLTP, which represents database transactional workloads. And here, we found that the two problems across these two, so we saw the slowdown in both these two benchmarks, but we found that the problems, the core cause of the slowdowns was actually two different reasons. And the second reason had to do with the way that basically that the metadata files are written back in terms of copy out. If you're familiar with the Linux details, basically the way copy out works, it was not functioning. It wasn't a bug, but the way it was working counter to the performance of the benchmark. And so we saw 25% performance improvements with our system. I refer you to the details. I have 2 minutes left, according to my clock. So let me just talk for a minute each on the big challenges that we had. The first is high variance. That blue area that you see is the single standard deviation around the points that we measured, right? So we had to measure things 50 to 100 times each for a single data point, which again increases the length of time that we have to do our experiments. We also can see lots of false positives and false negatives. So if you take a single sample across this space, you might conclude that performance is actually better at a higher frequency and worse at a low frequency, or the other way around. You might conclude that even though this line of average performance is pretty flat, that the best performance is at the lowest frequency. So that's a real problem for any kind of runtime management system, the kind of systems that we tried to build, where we change the clock frequency or anything that we're touching inside the system. The second thing is that it's very, very difficult to isolate these problems. The problem tracing the critical path across the software, the middleware, the hardware is very difficult. And so in cloud, it makes this even harder because there's more level of abstraction. So my last slide, with 1 minute left, is what I call my experimental wish list. So what would this system do? And I think a lot of these things y'all are promising, but having done it in the lab, I know it'll be difficult. So I asked a question earlier today for that reason, was that that's a difficulty that we've had, driver difficulty when we try to do such things. So mainly we need fine grain and coarse grain performance, both in band and out of band. We need access to that data. We need a variety of hardware, which I think you have. Heterogeneity across the hardware would be good as well. We need to be able to scale beyond just, say, 256 cores, or we can't test the scalability. And if things change, especially our fundamental understanding of the relationships of performance and power across these systems. We need a variety of OS and tools as well, and we need, just like the last speaker said, we need lots of access and control at the root level. Thank you very much. 10 seconds.
So one more from the UCs. This is from the beautiful San Diego. My name is. Hello. Can you hear me now? Yeah, my name is Amit Majumdar, and we have a lot of other people from the San Diego Supercomputer Center at UCSD, behind this two-page write-up. Mark Miller is actually behind a lot of the ideas we will talk about in the next 10 minutes. And Phil Papadopoulos is a network guy, and he had a lot of input and support from everywhere else. So we want to talk about science gateways, which are maybe all of you already know what it is, but I'll just explain in one line. It's basically a science portal for a particular science community, whatever community it is. So which provides at the back end HPC resources for that community without hiding all the complexities of HPC from them. For example, they don't have to write allocation proposal every year. The person who is running the science gateway takes care of that. So any user can get an account on the portal and just use the science gateway, whether it's for bioinformatics, for neuroscience, geoscience, protein folding, whatever. As well as we hide all the complexities, sending jobs through the queues, storing data and file system and all those things. So science gateways are very popular, I'll just pick two of them here because we are familiar with those two, but there are many other successful science gateways within the XSEED community, and I'm sure in DOE and everywhere, other places too. So the Cypress is for phylogenetics research, and Mark Miller is the PI of that, and Neuroscience Gateway is a science gateway for computational neuroscience. I am PI of that. Both of these are funded by NSF. And again, just with, there are many other science gateways, iPlant and, GridChem and many others. Just for our science gateway, we use this Workbench framework, but any science gateway will have like that, a portal to upload whatever the input files or data model, and in the back end, there are some HPC resources. Middle software can be whatever. In our case, we pick the one that we use. Again, just to show you how popular the Cypress gateway is, like about 30% of all XSEED users are from come through this Cypress gateway. And as I said, this is for phylogenetics research. And I think he has about 12,000 users. They have submitted about 400,000 jobs since 2009 on TeraGrid and XSEED research. For staff is 2 FT, but the centers for NSF fund, but there is a lot of other support. And as I said, you can see I think he has served about 65 million core hours in the last 5 years, so he gets 10 to 15 million a year. This gateway is a relatively new. It's the production year. The previous year was kind of thin. We used 2 million SUs, which for which I had to write a proposal. It went through the review, and we got the allocation. You can see the job sizes. Average job size is 200 cores, and and we burn about 50,000 core hours per month on the XSEED resources. So what I'm trying to get at is, NSF made all this investment in HPC resources, which is great, and these are mostly for machines which are which have fast interconnect, very fast parallel file system, and obviously tens of thousands to hundreds of thousands cores if you go to Blue Water. and mostly meant for codes which scales to many thousands of cores. Now, obviously, it has expedited the scientific discovery in bioscience and others. But if you look at the Cypress codes, they scale to 64 cores, and most of them scales to 8 cores. So, and the neuroscience is a little bit in both camps. There are neuroscience brain simulation that will scale to many thousands, but then they run parameter sweep type simulations which only scale to, which scale to small number of things. So the question is,
Actually, I want to interrupt you for a second. I've had a request that you switch to the other
Sorry. Here. Hello?
Sorry about that.
Okay, I can hold it here. Maybe that's the better. Yeah. Right. So the question is, what mix of high-end HPC resources and cloud resources is ideal for accommodating the science gateways. And as you know, in all the when exceed allocation review process, there is always oversubscription. Whatever amount all the NSF sites can provide, there is 3-time request. Again, both for neuroscience gateway, I know we ran out of allocations. We had to get for again allocation again. So the question is, and then there are some users from this phylogenetics community, at least, who are not coming through the science gateways and they need to find out why they are not coming, what is their needs, and can a cloud provider offer a low-cost solution for this user community? So the question is, when can we take the excess requirements or from these exceed resources for the science gateways, and can they burst out into cloud resources? So that's the question I'm trying to pose. And what are the issues? These science portals run some kind of software and a file system within a local site, whatever it is, say at SDSC. So can there be a private network connection between SDSC and the cloud resources, whether at Kate's cloud or Rob's cloud, where we can send these jobs, especially the single core jobs or appropriate jobs to those resources. And another is, we know, and what is the academic cloud that can provide, which commercial clouds cannot provide or don't want to provide? First, high performance network between users and the cloud. Is that something? I think that's probably not very, at a reasonable price, is probably not popular with Microsoft or Google or Amazon. So can the academic cloud provide a fast high performance network connection? Another is this VM for this science gateway, say the Cypress gateway, neuroscience gateway. Can we create a VM which will automatically adapt to the cloud computing resources provided by both commercial and academic, instead of again taking advantage of the network between the where the cloud science gateway is provided from and where the cloud resources are available? So, and in this way, we can free up the exceed resources for other kind of jobs, astrophysics, CFD, or whatever. So that is what we want to look at, is can we take jobs from the science gateway, which are highly popular, into cloud resources and look at what are the issues there may be. Yeah, that's it.
Hi, can you hear me? Yeah, it's fine. So my name is Rafael Ferreira da Silva. I'm from the University of Southern California, the Information Science Institute. And I'm here to present this work that is a collaboration of several people, people from Poland, people from USC, and some people from Notre Dame. I think it's passed automatically. So we have some, I'm gonna just give you a flavor of some research challenges we have here. And the main ones that we use, it's the execution of complex scientific applications on using workflows. So we have two main workflows management systems. One is the Pegasus one, developed at the USC. And the other one is the Hyperflow one, developed in Poland. Also, we have the analysis of the, deployment and share of scientific applications on hybrid clouds. So for this, we use the Atmosphere framework. It's a European project. And also analysis of algorithms for scheduling, provisioning, and cost optimization on clouds. So just to give have an idea, I'm not going into details for you for the Atmosphere framework. So you have some GUI the GUI, you have the users that go there, and users can interact with the framework, and you can have access to different kinds of clouds, like through OpenStack for the VPH share, it's a European project, and the Amazon EC2. Also, when we do simulations and scheduling for large-scale scientific workflows, we are dealing with hundreds and thousands of tasks. So as you could imagine, this can take so long to analyze if you use like small clusters. That's why we are looking for this this kind of infrastructure that we can play with a lot of different resources. And even though we use sometimes Amazon to execute these things, it can, as you can imagine, can be really expensive. So also you want to be able to execute workflow examples. That it's when you have different sets of workflows, many workflows. So it multiplies these numbers by dozens. And sometimes we use a lot of cloud workflow simulator because we don't have access sometimes for some cloud resources. Other type of research we do is the cost optimization of applications on clouds. So as you know, we need to do the infrastructure modeling. We try to model the infrastructure. We try to have some different kinds of applications, like just backup tasks or multi-level workflows. And we use some modern languages, mathematical modern languages, as the AMPL and CMPL. And we are trying to do some work, trying to say, okay, I have a cost optimization, so I have a deadline constraints. I need to do some optimizations in how I can scale it faster and better. And a fourth kind of research we conduct today, it's the performance evaluation. As I saw some guys saying already, they did some performance study. We also try to see the overhead on virtualizations using Eucalyptus, OpenNebula, OpenStack, and it'd be really nice to do this work in the NSFCloud. I'm really happy when you said, oh, you have access to really nice measurements. So we want to be interested on that. And we conducted some surveys on the European public clouds, but we also want to do this here if you want to work. So some experiments we want to try to conduct, evaluate, do the outscaling of the atmospheric cloud platform. So what we need to do, some challenges for us. Some difference with my phone. Sorry. Just put here. So some challenges. We need to repeat tests with different workloads. So this sometimes can be too much expensive to do it on public cloud. So that's why you want to go to this kind of clouds you are providing. And the most important one is the experience in an isolated environment. Because as you know, and a lot of people already mentioned, when you go to public clouds, you have a lot of workloads, you have a lot of noise, and you can't measure correctly the things what are happening. You don't know if the problem is if your code or if it's just a cloud noise. So this would be really nice if you could provide this isolation for us. And that's why I wanted to build this environment on this NSFCloud. Another one is how we deal with scalability on scientific workflows. So for now, when we try to use, especially when you use the Hyperflow model, we have a lot of challenges when you do data transfers and data locality. So we want to try to calibrate these performance models of these applications. So the idea is you want to try to execute this in multi-sites. And as always, you have different clusters in different universities. So it'd be really nice to analyze how we could schedule these tasks and see how it behaves for the network latency and bandwidth limitations. And it would be really nice if we could play also with this, play with this data, say, okay, I could reduce my bandwidth or I can increase my bandwidth. I don't know if it's possible or not. And we want to also analyze the influence of variability of clouds on the quality of our algorithms. We have a bunch of PhD students developing new algorithms, new strategies, new optimizations algorithms. So we want to try to be able to analyze these algorithms on these clouds, on these NSF clouds you are providing here. And as you know, we have a lot of uncertainties happening on the cloud. And we want to try to mitigate these effects of these uncertainties, measuring, especially on an isolated cloud environment. And as the last one, we currently use the PL grid. It's called grid, but it's It's a national grid cloud infrastructure in Europe, in Poland. And we use this as a cloud testbed for an open enabling of stack. And what you want to do is, using the atmosphere framework, run things at the same time on the Poland grid and on the NSFCloud, and try to transfer this data and see how we could make it this analysis faster and measure all these performances things. I know that if you can provide all these measurements on details, it would be really nice, because the Poland grid, we don't have these measurements so fine graded. So we could actually try to come up with a comparison and see what is the real measurement and what they are providing to us, and see how we could improve our algorithms. So I'd like to thank you, and if you have questions and you want to talk later, I'll be there.
Can you hear me? How about now?
You can also try it rather than hand over.
Okay. Okay. Good afternoon, everyone. I'm Mike J from Ohio State. Today, I'm going to talk about our recent project, reliability analysis framework for cloud storage systems. Actually, we are still in the very early stage of this project, so any comments or suggestions are more than welcome. So today we have many different data. Some are valuable and some are priceless. And we rely on storage systems to keep our data safe. So the reliability of storage systems is extremely important, as we don't want to lose any of our data no matter what happens. Most storage systems rely on devices as the lowest layer, such as the traditional hard drives and the modern solid-state drives. And many existing studies have shown rise for some. It's pointed out by Jeff Dean from Google. Are usually very complicated. Many sophisticated algorithms must be implemented correctly in each layer of the storage stack. So in a typical stack, and then run the user applications. Gaps of understanding of assumptions between different layers in a storage. Users full atomicity, consistency, isolation, or durability from the database. However, the database developers may sacrifice some properties for performance reasons. And also, the database developers may make some wrong assumptions on the behavior of the system call interface. And on the other hand, file system developers may implement a slightly different version of the system call interface. So all of these could lead to the reliability issues in the storage system. And so, and luckily we have a way to thoroughly analyze the reliability of local storage systems under So this is this slide shows the basic idea of approaches, and on top of our framework, we have careful such as control of the database, and then we have gather important function calls as well as system calls involved in the user space, and then in the file system level, we can probe the layout of the file system and gather information about the file. And then bottom of the so we can combine the static commands with the real patterns we observed in those devices to reproduce any failure state of a given device, and then we can use those failure states to test the behavior of any higher level software layer on top of the storage device. So this is a basic idea of our approach, and actually we didn't fully realize the importance of our framework until we implemented it. This slide shows can get from a local storage systems. For example, we can know the green line here is the function call recorded by our framework, and then the orange ones are the system calls, and the black ones and the black lines are the data block extracted from static commands, and the blue lines are the names of the files. So as you can see, by combining all of those information together, we can see a clear whole picture of the behavior of the local storage systems. Even without looking at the source code, we know that the database is very happy in their implementation. And then after showing the green light, they use fsync and nsync to commit their data to certain files. So based on this information, we have found we have pinpointed many severe reliability issues in the existing systems. So what we are trying to do next is to the framework to the cloud. So basically, any cloud management layer relies on local systems. So, and there have been many existing studies on the reliability of the cloud systems, and most of them focus on testing the cloud systems under certain failure conditions, and almost all of them consider three types of simulated failures, such as message reordering, machine crashes and reboot, and network partitioning. And of course, these are real problems in the cloud environment. What we are trying to do is different. First of all, we have a more fine-grained local failure sequence based on our previous studies, and also we are more interested in the failure propagation chain along the whole data path from the local to the cloud. Where based on our experience on the local storage systems, the whole picture of along the whole data path will be very helpful for diagnosing or for understanding the behavior of the system and the root cause of any failure sequence, and for tuning the performance of the given systems. So this is our goal. And from a test bed is on the hardware side, we need different types of local storage devices, including traditional hard drives, solid state drives, or hybrid systems. And because different storage devices have different failure modes, so this is what we need to consider. And also, we would like to the hardware rate layer storage systems, because many commercial production systems has hardware rate So we would like to test some systems that are way closer to the production system. On the software side, basically, you need to have the capability to control every software layer along the data path, including the iSCSI driver. iSCSI is a protocol that allows us to transfer SCSI commands over a network So we build our framework on this layer. So it's very important layer for us. And other layers such as local file systems and local backend databases, those are layers as well. So an important service is the synchronization service, because we need to claim multiple events for multiple nodes. And I think this is a useful service for many cloud systems. So that's it. Thank you.
All right, thank you. I'm Gerald Baumgartner from Louisiana State University. To introduce myself, most of my research over the last 50 years or so has been on domain-specific language and file optimizations for high-performance computing, in particular quantum chemistry and tensor contraction engine. What I'm trying to do here is make complications like that work in the cloud. So the motivation is supercomputers are very often too expensive for scientific applications, especially if they will be loaded enough. Rented clusters in the cloud are also expensive. Amazon, they are on the order of a few dollars a compute hour. On the other hand, rented virtual machines would be cheap, but they really only work very well for MapReduce. That's maybe a bit of an exaggeration. We've seen lots of other good frameworks that are out there. But the problem with VMs is they are very unpredictable. I don't know how many VMs might be on the same physical machine. If I want to run a distributed application where two VMs need to communicate and have very tight synchronization, that's not going to work too well if they're running on the same physical machine. And also the communication latency is oftentimes very big. So the goal that we are trying to achieve is to make use of cheap rented nodes wherever we find them. Measure the performance of the machines and of the network that we get. In part, maybe if we have a system software available installed that we can query, otherwise actually runs short benchmarks. And then try to place the compute tasks where we get the best bang for the buck, where we get appropriate performance for the needs of the task. So the cloud framework we are proposing is that either cloud or physical nodes will contain measurement tools to measure their own compute and networking performance. That these performance measurements are distributed throughout the network or on some overlay network. What I'm envisioning here is something along the lines of routing table updates, where aggregate information is distributed so that every node knows where to find which type of resources. And then applications can dynamically, applications would be structured as task graphs, where an individual task might be running on a single VM, or it might be a distributed task that's running on a small set of tightly coupled VMs, and there may be dependencies between the tasks, and some tasks need to be computed before others, and then applications select the most appropriate nodes or set of nodes for each individual task. In order to be fair, in case of competing applications, nodes will have the opportunity to reject tasks. The idea is similar to a recent patent in my VM, the traffic Java virtual machines for that. Why? Because we'd like to experiment with these distributed scheduling algorithms and including migration and migrating objects in Java is a lot easier than migrating entire virtual machines. So we would use mobile agents in Java as the management software that carries the computational payload where the resources are. So in relating this to air traffic control, those mobile agents would be the pilots. And we have technology to provide strong mobility where agents can migrate with their running computation. And that would allow us to fairly easily implement migration at relatively low development effort of the application programmer. And as a demo application, we'd like to use quantum chemistry simulations. In quantum chemists, they can scale their simulations to just about any resources you give them. For example, at supercomputing, last month there was a paper where they demonstrated scalability to 50,000. For experiments, the initial experiments would be to develop testing tools for testing the performance of nodes and networks and to test those testing tools. And then later for developing and testing the distributed scheduling applications or migration decisions, and only eventually, maybe further down the road, test it with real scientific payload. And for some of the tests also, what would happen if there might be a competing application to another payload running on the same system. The experimental needs we have for this are a variety of different cloud resources which are provided here. The ability to have both dedicated nodes as well as nodes shared with other workloads or with simulated workloads, and access to storage for intermediate results. On the software side, it's pretty minimal. We need Linux, Java, and maybe some quantum chemistry tools that they might need to install. So to summarize this, we are proposing a framework for matching application needs with available cloud resources that's based on measurements and then distributed decisions of which task runs on which resource, and then run decentralized task scheduling with work scaling. Thank you. And might have finished maybe a few seconds before time was up.
I hope everyone is still awake. So my name is Abdulmanam Rezki. I'm from New Mexico Tech, and I will talk about ad hoc cloud-based computing clusters for big data processing. I didn't know I could go very technical, so you won't see experiments. So I tried to adhere to Kate's recommendations. It's not working. Okay. So this is actually a project that's supposed to start next month. So it's still in the beginning. So briefly, my research area essentially is in the area of volunteer cloud computing to support big data science. And the specific problem that we are trying to work on is how to build efficient distributed cloud clusters the fly for given big data applications. So essentially what this means is that we have the application first, and we are trying to build a system that can automatically generate a distributed cluster to support this given application. So this will be, two research questions. So first of all, can we actually do that? Can we take a big data application and generate given test bed like Cloud Lab, for example? Can we build a cluster that can support the execution of this application efficiently? And then if we can do that, then how can we synchronize the activities? How can we synchronize the execution of this application? And we'll come back to this point later to achieve good performance. So doing this is obviously important. So what we want essentially is to make it easier for big data scientists to have access to large computing capacity and storage capacity, like many other speakers said, so at a low cost. Challenges. So first of all, we are talking about resources that are essentially donated, so they are free, but at the same time, they are their availability is unpredictable. So how can we do resource allocation, given that we don't even know how long these resources will be available, how much they are reliable, and so on and so forth. And the other thing is that we need to essentially formulate the entire problem as an optimization problem. What's the best cluster to solve a given big data application? So, and we can have thousands of different possibilities. So how can we choose the best out of these alternatives? In terms of experiments, so we thought about some, but these are just some examples. So the first one is that we would like to run on top of the future test beds is how to prove that we have an optimization framework that produces suggested clusters. So how can we actually make sure that this framework actually is giving us what we want? So good configurations of nodes, so good locations and good configurations. So the way we are planning to do it essentially is to try to manually build distributed clusters and then run the big data application on top of these clusters, and then compare the performance that we get from these executions with the performance that we can get using the configuration produced by the optimization framework that we will develop. The next experiment is studying the overhead. So we are already talking about big data applications that can run for hours or days. And if we add to this the fact that we are actually building an entire computing cluster after the application is submitted, so that's an additional overhead, and we don't want to delay things even further, right? So, so the second set of experiments essentially aims at studying the time that's spent between when the user essentially submits a big data application and then the time when an optimal compute cluster is ready and set up to run the application. And then the third I guess last experiment is to determine the best interleaving that's possible. So what we call the best choreography. So remember, very intuitively, so we have a big data application that we want to run remotely. So intuitively, we can think of this process as a sequence of three things. So first of all, forming and building the cluster, and then loading the data on the nodes of the cluster, and then running the application. So obviously these three tasks, they don't have to be executed one after the other, right? So maybe there is some interleaving that can happen. So the third set of experiments will go into essentially studying the best way to interleave these activities to achieve the best level of performance. And then I will just conclude by two slides here related to the capabilities that we would like the future testbed to offer. First thing is, an API, essentially. We all like to code, right? So this last month, one of my students sent me an email and he said, Jenny is a nightmare. And he had been working on a semester project for a while, and he essentially had to do a lot of configuration, and he had a lot of problems. So students specifically, they prefer to program. So it would be a good thing to offer an API that users can use to, for example, create just through programming an entire computing cluster that they can use to select locations for given sites, for given nodes, that they can use, for example, to grow or shrink the size of the cluster at any point in time while the application is running. Also, the API would give the programmers the ability to transfer data from where the user is to the nodes, and so from and to these nodes, and so on and so forth. Also, automatic VM deployment. So I guess some of the speakers already touched upon this, so no need to waste time on this. And then 3 more things: location visibility. So once the cluster is formed, so we would like the test bed essentially to be transparent, so to show the users essentially where the nodes are, maybe also other specific characteristics of these nodes. This obviously would help. Also, because we are talking about big data applications, so they run for maybe days. So obviously failures could happen. So we would like the test bed to be also transparent with regard to this to fault tolerance. And here, essentially, I mean transparency in the other sense. So in the sense that users should not really be aware of all of these failures and the way the system is handling them. And then finally, the last point is the repeatability. So obviously, if we are running this lengthy experiments over and over, so we want to have some stable results, and to have a system that actually more or less give similar results when we repeat the experiments, so that we can have some level of confidence related to the experiment. I guess I'm done. I went too quick, maybe.
How's that? Can you hear me? Oh, right, you can. Can everyone else hear me? All right. So I'm Martin Swaney from Indiana University. I'd like to thank the organizers for inviting me, and I'd also like to say that I'm really excited by the what we've heard today. I think this is going to be great infrastructure, and I'm looking forward to using it. And I think maybe it's possible that you read the white paper, but it's also possible that you just already anticipated everything that I wanted. I should have been, so I'll try to on the fly throw in some maybe more problematic things, just so you guys don't. What's that? Yeah, exactly. You anticipated it, so it's great. So let's see. I have been PI of 2 Genie instrumentation and measurement projects. And PI on the Genie Experimenter Award. So I've been involved in the Genie world for quite some time. When I moved to Indiana, I got involved with Future Grid, and I was able to do some of what I called Swaney defined networking, which is rewiring one of their clusters in the data center. Fear it? See, you thought something else, probably, didn't you? I really, I've sort of seen the arc of this thing, and I think this is great stuff. And also, I'm going to talk about, I was in the Genie mindset. I was in the network research mindset when I wrote this. I think some of the things that Jack mentioned, we're also working with parallel runtimes on top of the Kitten lightweight kernel at IU, and the things that he was mentioning in terms of the sorts of access. I didn't even, that wasn't even in my head, and I think that that's really encouraging. I think the idea of a reference platform is also a really good one, and I have to say I went and ordered about 5 minutes after Rob's talk, I went and ordered 2 applied micro X-Gene boards. So, because, okay, one of my problematic things is if you're going to develop at that level, you're going to need a JTAG interface maybe so that you can single step. I don't know how, if you guys have plans with that through the moonshots. Yeah, but that's the level at which you just need a box, like Jack said, that you can take home, and and also when talking about FPGA-based acceleration, that's hard enough when it's on your desk with the JTAG module directly attached to your system. So interesting questions about that, but still exciting stuff. So I'll talk about this world at a high level. I followed the directions too, mostly. No, I did to the letter. 2 distinct experiments. High level, why it's important. It's important because we need to evolve the network architectures for distributed computing. I think that's pretty well understood. Our approach to evolving them also involves having them adapt rather than sort of one size fits all. Our sort of general approach is measure network performance, sense the network, which is what led to my involvement in the development of the widely used perf sonar measurement network measurement system, Periscope, which we developed in the Genie context for INM, the Network Weather Service, which I worked on when I was a grad student back at UCSB. Then we want to reason about the network. We want to build models of the network that capture with the right amount of expressiveness what's going on. Generally, this sort of means squashing, beating on it until it's a graph that we can approach with some well-known, graph algorithms, and then adapt, either alter the network topology or alter the way the protocol is working, or translate the protocol transparently in the network, and sort of, and then lather, rinse, repeat, trying to build smarter networks that can do a better job. And so the 2 things that I'll talk about are related to one of our projects called the Data Logistics Toolkit, which is a CCNIE integration with Tennessee and Vanderbilt. And we've been talking about logistics, data logistics, for a long time. The need is growing with sort of the growth of data. Logistics means this, and we were talking about it before UPS went on their massive ad campaign, which helps. This is obviously a critical problem, so considering data where it is, and the DLT integrates shardable storage, file transfer software, network acceleration, performance monitoring, and the ability to interact with dynamic networks. So creating data distribution and transfer overlays. The 2 things I'll talk about are sort of related to that. First is Phoebus, which is an open source WAN accelerator. I spent years explaining what this was and being heresy in the church of the end-to-end argument, and now you can just say it's a WAN accelerator. It's a $2 billion industry, and this is a free one. And going back to sort of the overall flow, we take measurements. Some measurements from some point indicate that the direct TCP connection is not doing as well as it could. So we want to locate or maybe spin up a Phoebus gateway, alter the network topology if necessary, so that we are creating either private networks or rules that allow us to shunt traffic through the Phoebus gateway. Ideally, what we like to do these days is to create traffic engineered layer 2 paths with software-defined networks of some sort, and then burst with RDMA over Ethernet and over those paths, Rocky. Once you've engineered the network, or you've created a virtual link, you know what the performance is, then you can very efficiently go with non-IP memory-to-memory transfers. And we also would like to do that rather not necessarily consistently, but treat the Phoebus gateway's DRAM as a giant burst buffer, fill it up, allocate very quickly a circuit, burst over that circuit, and continue to do that. Again and again, sharing sort of a different layer, burst switching sort of rewritten in a different way. This would require high-performance software-defined networks. I'm glad to hear that the networks that were described are just delightful. I was just smirking like it's almost Christmas. That's exciting. And or either a bare metal machine. I know that. I know, indeed, it's true. Either a bare metal machine or a tuned VM. SRIOV has been mentioned extensively, so we're looking forward to that. What can we say about some of the problems? Okay, in software-defined networks, one of the big issues is the frequency with which you change rules. So the number of flow mods, and there's a potential for denial of service. And there's a place where performance isolation is actually extremely tricky. So bare metal switch control is one way to go about that. So a lot of things we would like to have high rate of flow mods and fine-grained flows. Also, being able to signal across AL2S is a great thing. Has anyone tried it? I know a couple of you, and I know you also know what I'm saying. It's, there are going to be issues stitching all these things together. Right now, running your own slice in AL2S involves a vetting process that, you know it? No one knows it. It involves a vetting process of them looking at your code, maybe, and trying to decide whether it, halts or whether it's going to crush the network. I don't know. They don't know. And these people are, at my university. They don't know. But they're doing it. We got certified to do it, but I don't know that anyone else has. And it wasn't easier because we know them. In fact, it was probably more difficult because we know them. But I don't know that, so they're talking about how they're sort of doing it. They're sort of doing it. What you can do right now is go to a web page reliably and get a layer 2 path. And they're working hard. I'm just saying there are problems. There are significant problems in terms of a performance isolation that these guys who are running a production backbone that you can also do experimental stuff on are extremely sensitive to, as they should be. Right, those are interesting things. It sounds like, though, a lot of them will be addressed. Okay, the other thing I'll say about a Phoebus experiment is what we'd really like to do. Real latency in the real WAN is good, because if you don't do that, then people will say, oh, you just played in your simulator or your test bed. And if you only, but what you also want to do is sort of parameter sweep across different latencies. So it'd be nice to have a canned latency generator. And in, sort of FutureGrid had one of these, but you could emulate a single 10 gig link, which is no longer sufficient. And we had to do the other thing that I'll say is there's been a lot of talk about sort of encapsulating things into APIs. That's problematic because that takes a lot of time, and then some person like me always wants to do something that's just beyond what the API can do. We had this problem in FutureGrid. There was this nice network device that the signaling mechanism was open a ticket with the global knock, and we had to explain to them first, gently and then less gently. You don't know how this works. This is a grad student at 2 a.m. 5 things, and then no, wait, I need to roll it back to 10 milliseconds. Wait, did that work? No, crank it up to 50. So the control interface, we ended up writing one. It can be, it can be productized. I'm hurrying. Second experiment, which is different, is using the DLT for something we call the Earth Observation Depot Network, a collaboration with AmericaView, works with USGS and USGS to distribute Landsat 8 satellite imagery. This is the thing that we're investigating in another Genie Experimenter Award that's PI'd by, I'm a co-PI, it's PI'd by Ezra Kissel. This requires long-running partition of resources with good external connectivity. So this has been kind of problematic in the current Genie world. Paul's been very helpful in getting us last time good external connectivity, because it was sort of envisioned these are all, we have good access to one another, but not to the outside world. So the ability to provision a long-running slice with good external connectivity is something also that's been mentioned today. And then measurement, key problem with experimental systems work. This has been talked about, but also, even having been involved with Genie I&M, I can say it's always a problem to get the measurements that you need at the fidelity that you need and in the location that you need to be able to write a systems paper that doesn't have sort of question marks of, man, we don't know why that blip was there. And also some of the measurement, even if you create a span port to duplicate traffic, on a switch, that can have performance implications. And sometimes, that's why I have a bunch of fiber splitters on my shelf that, occasionally we need to use. If you need completely transparent, high fidelity measurements at that level, sometimes you've just got to do it physically, and that's going to be tough to automate through, Vegas. So that's my story. Thank you.
Okay, thanks everybody for the presentation. Thanks everybody for reading my instructions. In particular, thanks to those who followed them. I just want to say, miraculously, somehow, we're actually on time.